So, hi everyone. Welcome to our weekly seminar here at the Institute of Astrophysics in Crete. Today we have the pleasure to have with us Dr. Jorge Otero-Santos. So briefly about Jorge, he obtained the PhD degree at the Instituto de Astrofísica de Canarias and the Universidad de la Laguna in Tenerife in 2023. And after that, he moved for his first postdoctoral appointment to Granada at the Instituto de Astrofísica de Andalucía. Now he works as a postdoctoral fellow at the Istituto Nazionale di Fisica Nucleare, INFN, in Padova, in Italy. His research focuses on the understanding of the multi-wavelength emission in active galaxies and in particular in blazar, using photopolarimetric data from optical to the highest gamma ray frequencies. He has been part of the MAGIC collaboration since 2018, and he's now deeply involved in the Cherenkov Telescope Array Observatory, CTAO, Science Consortium, and also in the LST collaboration that is in charge of the commissioning and operation of the large-sized telescope prototype, LST-1, that I see here in the title. So Jorge will tell us a bit more about this. And within the LST collaboration, he's the coordinator of the extragalactic physics working group. So thanks for being with us, and the floor is yours.
Thank you very much for the invitation and for the opportunity of giving this talk. And we'll be presenting briefly some overview of the present and future of gamma ray astronomy through LST-1 that is already operating. So therefore the present, but also future. What CTAO will bring to the table in the near future. And I'll be presenting briefly also some first results on the extragalactic science that have been obtained with LST-1 in the last few years. So I'll be briefly introducing the gamma ray sky and Cherenkov astronomy, CTAO and LST-1, and then I'll be discussing briefly some of these results. I will also try to give some overview on some of the tools that we've been developing for this new generation of telescopes, especially in this multivalent context in which we always support our gamma ray observations, and a few perspectives on physics that we will want to do with CTAO. So this is as a starting point, an image that you probably are familiar with. It's the gamma ray sky as seen by Fermilab after 16 years of operation. And one thing that we already see is that, well, apart from the highly populated galactic plane, where we have a lot of extended sources, diffuse emission, complex morphologies, once you go away from this galactic plane, we are basically dominated by point-like sources. And these most of these point-like sources in the extragalactic sky are active galaxies, AGNs. So we start having a first clue of why AGNs are important in the gamma ray domain. And these are basically galaxies hosting a supermassive black hole in their center that is, as you see in the figure on the left, that is basically accreting matter through an accretion disk, and has develops in some cases these other structures such as the dusty torus, these molecular clouds, broad-line and narrow-line region, etc. And some of these develop also these highly collimated relativistic jets. As I said, most of the sources in the extragalactic gamma ray sky are AGNs, but even within those AGNs, most of them are blazars. Blazars are simply AGNs in which the synchrotron jet, this relativistic jet, is pointing closely in alignment with our line of sight. And they are characterized, their spectral energy distribution is characterized by this double peak structure that you see on the figure on the right, with synchrotron emission explaining the low energy peak, and different processes involved in the or debated in the high energy emission of blazars. So what can we do, or what can we expect to, what information to expect to obtain from gamma ray observations of blazars? First of all, and you see in this image the cosmic ray spectrum, and we know that above a certain energy, most of the cosmic rays that we observe have an extragalactic origin. We simply do not see galactic sources as the main source of these ultra high energy cosmic rays. So this is, for instance, one of the studies that we can carry out with this kind of observations. Also, studying the formation, collimation of extragalactic jets from these supermassive black holes, and the processes that are involved in the emission of gamma rays that, as I said, are still debated and are interpreted sometimes with a leptonic scenario, sometimes with a hadronic scenario. So this is another important key of information that we can obtain from gamma ray observations. In synergy, for example, with what IXP has brought to the table in the last 2-3 years, we can study closely the location of the gamma ray emission and the processes involved in the acceleration of particles that ultimately result in this gamma ray emission. Blazars have also, and AGNs have also been the most promising candidate, for instance, for extragalactic astrophysical neutrino emission. So this is another thing that we can do with gamma ray observations, this connection between neutrino emission and multi-wavelength emission of blazars, and even some more exotic, let's say, topics such as, for example, dark matter searches or dark matter constraints, searches for action line particles, or cosmology with through gamma ray observations. So there is a lot of things that can be done with these sources at very high energies. And for this, the lab has been basically leading the effort in the past 16 years in the MEV to GeV regime. But what happens when we want to go to higher energies? So at GeV TeV energies, simply the astrophysical fluxes are very low. So for us to detect something from space, we need to launch an instrument that is simply too big for our capabilities nowadays. So we need to basically build ground-based telescopes, these Cherenkov telescopes that use the atmosphere as a calorimeter. So whenever gamma ray interacts with the atmosphere, creates this cascade of secondary particles. When the primary particle is a gamma ray, it's basically electrons, positrons, and more photons. And these particles travel through the atmosphere faster than the speed of light, creating this very fast and dim Cherenkov flash. That is what our telescopes record, and create these elliptical shapes in our cameras, as you can see in the picture of the left. And through the parameterization of these images, we are able to reconstruct the information of the incoming gamma ray, mainly its direction, energy, etc. So we have developed this technique, this IACT technique. So we are able to access the most energetic universe that through space-based observations we simply cannot, because we don't have the technology to do it. And in the last 2 decades, more or less, the efforts have been led by the current generation of Cherenkov telescopes, namely MAGIC in La Palma, HESS in Namibia, and Veritas in the US. And this current generation has been really groundbreaking for the field. You see on the graphic on the right that up to this third generation of ICTs, we barely knew in the early 2000s like 10 to 12 sources able to emit in the GeV-TeV regime. And right now, it doesn't sound, in comparison with other facilities as Fermilab, it doesn't sound that much, but we managed to discover so far over 300 sources emitting in the very high energy regime. So these telescopes have been really groundbreaking for us in this topic. And this is how the very high energy gamma ray sky looks nowadays. Still, of course, not as populated as what Fermilab sees, but we are already increasing a lot our knowledge of the most extreme universe. But the future, as the title of the talk said, goes through the Cherenkov Telescope Array Observatory. Here you see an artistic image of how the observatory will look like in the near future, in the two sites that it will have. It will have a northern site, CTAO North, again in Spain, in the island of La Palma, and a southern observatory in Atacama, in Chile. And it will consist on telescopes of 3 different sizes, each of them optimized for observing in a different energy range within the GeV-TeV band. And the important thing that and the important feature that CTAO will bring to the field is a sensitivity increased by an order of magnitude, which will really revolutionize the field. And also, it will have a wider energy range that will allow us to observe soft and very soft sources that we have not been able to detect so far with its lower energy threshold with respect to the current generation, but also it will allow us to go to even higher energies than before. And now I want to focus a bit on the northern side, because it's basically the one that is most advanced in its construction. Here you can see on the left just a display of the observatory, and on the right is a picture taken very recently, actually like 2 weeks ago, by one of our colleagues in the collaboration. And you can see how advanced the construction of the 4 telescopes of the large-sized class is already on the site. And actually, the LST-1, the first prototype of the large-sized telescopes, is already built and operating since a few years ago. So since 2020, more or less. And it is, as I said, the first telescope of the northern array, of the large-sized telescope class. It has a mirror of 23 meters of diameter, which makes him very, very optimal for the let's say low energy end of the very high energy band. So in the energy range of a few GeVs up to a few hundreds of GeVs. And not only that, but it already has a smaller energy threshold than the current generation. So it can go down, the LST-1 alone can go down to around 30 GeVs. And this is especially important for for some of the key goals of CTAO, and especially for expanding the knowledge or expanding the boundary of the observable very high energy gamma ray universe. And this is basically because our observations are strongly affected by the attenuation that the extragalactic background light produces on the gamma ray emission of extragalactic sources. Basically, DCBL, this extragalactic background light, is just a diffuse collection of photons from the history of star forming in the universe, and they can interact with these incoming gamma rays, creating these electron-positron pairs, but more importantly for us, attenuating the intrinsic gamma ray emission of our sources, as you can see in this couple of examples on the right. And this attenuation is more important as we go to higher energies. So the higher the energy of the photon, the higher the attenuation will be. And not only that, of course, the farther the source is, the larger is the probability of a photon interacting on its way to us, simply because it has to make more distance until reaching the Earth. So it is also more impactful for more distant sources. And this is why so far we have let's say a boundary of the visible very high energy universe at around redshift 1. And one of the key goals of CTAO is breaking and expanding this boundary. So if after this brief introduction of what is the current state of the field and what is CTAO and LST, I'll be presenting some extragalactic observations with LST-1. And LST-1 actually has been devoting already quite a large number of hours on AGN observations since the very early days of its commissioning. And it has already detected a lot of sources at GeV-TeV energies. Most of them were already known by the previous generation of telescopes, because of course, still with one telescope, the capabilities and the science that we can aim for are still not as powerful as it will be, as they will be as soon as we have the 4 LSTs built and operating. But these results are a perfect proof of concept and a perfect proof of the very good capabilities of LST1. So as a brief summary, for example, we have 2 of the favorite targets of the current generation of telescopes, and especially of those located in the Northern Hemisphere, namely MAGIC and Veritas. One of them is Markarian 421. Those of you working on the Blazar field, this source is for sure familiar. And this source has been regularly monitored by LST1 between 2020 and 2022, and it has devoted quite a few hours on it. And during May 2022, we actually got a very interesting flare, peaking at a flux of three times the flux of the Crab Nebula. For those of you not familiar with this, we always use the flux of the Crab Nebula as a reference, because it is our standard candle in very high energies. As we know, it is a source with constant flux. It doesn't change, so we use it as reference. And one of the important features of this flare was the very fast, very high energy gamma ray variability that we managed to observe. And these kind of events of minute scale variability at very high energies are actually very important for us, because first of all, they are not common at all. We usually don't see such fast variability in very high energy gamma rays. But second of all, they challenge the current knowledge of particle acceleration and emission processes in blazars, because usually they require very extreme conditions for this variability to happen, and they are usually linked to either shock acceleration processes or magnetic reconnection, for instance. So it is a very interesting event for testing, for putting into test these kind of scenarios. Another example is the other Markarian, the other typical Markarian for gamma ray emission, Markarian 501, that has also been monitored in this couple of years. And another important thing that we can do with these kind of sources is studying their spectral variability. And in this case, Markarian 501 has shown very clear spectral variations in the very high energy gamma ray domain. And this is again very important, because we don't usually have such a well-constrained spectral variability, and it comes and it brings to the table a very important piece of information that is characterizing very well the underlying particle distribution that is responsible for the emission, and how it changes, which is ultimately important for interpreting the emission within the typical scenarios for gamma ray for broadband emission of blazars, and trying to test for example, leptonic and hadronic scenarios. Other targets that have been detected with LST1 are, for example, these are the 3 sources. One is 0647, PG 1553, which is also quite among the preferred targets for MAGIC, for instance, due to this likely periodic emission that has been observed in the high energy gamma ray band by Fermilab, or 1ES 1959. And for example, for the 2 first ones, 0647 and PG 1553, this is also already a good proof of the performance, because they are already quite distant sources. Understanding by distant, taking as as reference this boundary of redshift 1 that I was mentioning before. So for us, having a source at redshift 0.4, 0.5 is already quite challenging in many cases, because unless they are very, very bright, their gamma ray emission is already highly attenuated by this CTL. So detecting these two sources in just a few hours of observation is already a very good proof of the good performance of LST1 at low energies. And as I commented at the beginning, either if most of the AGNs that we know at gamma rays are blazars, radio galaxies have been also observed very frequently with the current generation of Cherenkov telescopes. And actually, LST1 has continued this program on radio galaxies. And they are actually, apart from known very high energy gamma ray emitters, they are also very, very interesting because unlike blazars, radio galaxies don't have the jets pointing towards us. And this comes, of course, with the disadvantage of not being that highly relativistically boosted, but also with a lot of advantages that blazars simply don't have, because we do not get to resolve the relativistic jet as we do for radio galaxies. So for this kind of sources, we basically get a lot of information on how the jet is developed, how the emitting regions are distributed along the jet, and so on, by observing them at different frequencies, as you see here in the picture that I included on the right. So they typically have, first of all, very well-known redshifts and a very visible host galaxy, but also very rich and populated spectral energy distributions. Also, given the fact that they are very easy targets for radio telescopes, we typically know from radio observations their Doppler factors, which is a very good advantage when it comes to interpreting and modeling their multi-wavelength emission. And they also often show these powerful, very high energy gamma ray flares. However, they are sometimes challenging for triggering, because we typically rely on external alerts, mainly from Fermilab, but these kind of sources are not always very bright in the high energy band. So this, as I said, comes with a series of advantages, but also disadvantages. And I'll be talking for a couple of minutes on the observations that LST1 has performed, in particular on the Perseus cluster, which is the cluster that you can see here in this image. And in this cluster, there are two of the plethora of galaxies that are known very high energy gamma ray emitters. And these are NGC 1275 on the left and IC310 on the right. And these two galaxies are actually very interesting systems. First, NGC 1275, it is not actually a single galaxy, but an interacting elliptical and spiral galaxy system. It was already detected by the MAGIC telescopes back in 2010, and it has been used for several different types of studies. So dark matter searches, cosmic ray studies, intergalactic magnetic field studies, etc. So the usefulness of this data has been really, really amazing. And as I said, it has shown in the past several outbursts and flares, such as the one detected here by MAGIC in 2016-17. On the other hand, IC310 is a lenticular host galaxy with a strongly bent jet. And this one is also very interesting because it has shown in the past a very, very bright flare, peaking at a flux equivalent to even 5 times of the Crab Nebula in 2012. And these very huge and very fast variable flares, as I said before, come with a lot of information for modeling and the gamma ray emission and the morphology of this emitting region. And LST1 has devoted more than 35 hours of observations to this Perseus cluster, which for us, in addition, is very convenient because both of these two sources are located within our field of view. So we have observations of two AGNs by the price of one, basically. And this is the case of NGC 1275, which we started observing in December 2020, when we observed this very nice flare with very fast variability, actually. You can see in the light curve on the left that the flare peaks and decays very fast by a factor 3, more or less, during the same night. So we really managed to catch a very fast developing flare that will bring a lot of information to the table when trying to interpret this emission. And not only that, but over the whole period that we have observed it, up to 2023, it has shown very clear spectral variability, which again brings a lot of information when trying to interpret the underlying particle population that is responsible for this gamma ray emission. And this is how the sky map of the region looks for us. So we have a clear detection on AGC 1275. However, when integrating the whole set of data, we do not really see a clear signal from IC310. However, during the night of the 8th of December 2023, we caught IC310 in a flaring state while observing NGC 1275. So again, we have very nice observations to interpret these very fast and bright flares in these radio galaxies. On the right, for example, you see the spectral change from the average emission state over the last couple of years for this source with respect to the night of December 8th to 9, 2023. Now moving to the last part of the results, I wanted to spend some time on the target of opportunity program of LST1, which has been actually very, very strong in the last couple of years. So we basically rely, as I commented before, on external alerts from other facilities, mainly Fermilab, through a couple of automatic analysis pipelines that we have incorporated in our collaboration, in order to catch these transient flaring states from blazars. And one of the most successful and also one of the projects that I'm involved in within the collaboration is based on the observations of BLSRTI. This, again, is one of the most common sources in blazar studies, and it has been detected several times at very high energies, but always on a flaring state. We have never detected so far BLAC on a low emission state. And this source has been showing for the past 4 years, more or less, since 2020, actually, this series of outbursts, of very, very bright outbursts that, as you see in this light curve, have no precedent for this source. And in particular, LST1 has observed these two major flares in 2021 and 2022. Here I'll be focusing on the second one, as I'm the one. It is the one that I'm involved in, and this has been not only a very long-lasting flare, but among the two brightest flares of BLAC, not only in the gamma ray band, but in basically every wavelength. And we have characterized its average emission. You see on the right the average gamma ray spectrum as seen by LST1, and this has allowed us also to construct the light curve. And you see how variable the source was over this long-lasting flare between September and November 2022, with an average emission more or less on 20% the flux of the 25% of the flux of the Crab Nebula, but peaking up to more than 2 crabs actually when going even to a finer beam. This would correspond to night-wise observations. And in particular, we see these two brightest nights in October 2020, October 20, sorry, and November 13th, that are especially important because, again, we see this minute scale variability in its emission. This is the example for the night of October 20, where we see the emission peaking at 4.3 grab units and variating more than a factor 4 in less than 1 hour. And we can resolve actually through this large typical light curve modeling of exponential rise and decay profiles, doubling flux time scales as short as 3 to 4 minutes, which really puts heavy constraints to the size of the emitting region. It has to be a very, very compact region within the jet. And this actually is very interesting because, again, it challenges very hard current theoretical models of blazars. Usually, acceleration processes taking place in blazar jets have troubles to explain this kind of very fast variations in the gamma ray band, and they are usually accommodated within magnetic reconnection scenarios. Otherwise, they just need very high, extremely high Lorentz factors that radio observations simply don't support. And for understanding precisely this broadband emission, we have collected as much multivalent data that we have been able to. This is the collection of data that we have gathered, and we already see a few interesting things. First of all, in the X-ray domain, we see this softer and brighter trend that is basically indicating this transition that you see also in this plot here on the left of the X-ray emission to inverse Compton dominated, so already in the high energy peak of the SED, to synchrotron dominated, so in the low energy peak of the SED, which is, it has been observed for this source in the past, but it's a feature that is not so oftenly seen in blazars. And again, it brings a lot of information about the particles responsible for the emission. And this shift of the X-ray emission towards the synchrotron is also accompanied by this shift of the gamma ray peak of the SED towards higher energies. So you see here an example of this joint LAT and LST1 SEDs, and you see clearly how for the highest states, the peak of the SED is shifting towards TeV energies. So with all this rich data set, we are trying to do a sort of time-dependent modeling of the SED because we really want to understand how this flare developed and evolved. So we are using a leptonic scenario. This is favored by latest IXP results on this source. And we have tried several alternatives. We saw that one-zone leptonic models simply do not reproduce the emission. And we have then a couple of possibilities. So either one zone with external Compton that could be feasible, but would need an emitting region very close to the black hole and extremely high Doppler factors, which are simply not supported, or two-zone models. As this is the one that we opted for. And we are basically interpreting this two-zone model as a magnetic reconnection motivated scenario. So the intranight very high energy gamma ray variability that we observed and most of the very high energy emission would be connected to these small compact regions that would be the magnetic reconnection regions that are basically interpreted at this typical mini jets in a jet scenario where a compact region of the jet is closely aligned. So it would be misaligned with respect to the direction of the jet and closely aligned with our line of sight, being even more relativistically boosted than the bulk of the jet emission. And these models are still preliminary. We are refining the results, but you can see clearly here the evolution on three snapshots that I just chose from all the models that we have for the development of the flare, and you see how nicely the SED is evolving during this 3-month period. And the last result that I wanted to comment, and this is actually one of the milestones that LST1 has accomplished so far, is the detection of the flat spectrum radio quasar OP313. And this is important for several reasons. First of all, it is only the 10th flat spectrum radio quasar blazar type source that we have detected ever at very high energies. So far, we only knew 9, and this is only the 10th one. So this source type is really elusive for us, and it is important to increase the number of sources that we detected at very high energies to increase our knowledge on these sources and to understand why we do not often detect them. Second of all is also the first scientific discovery of the LST-1, proving its good performance, but also it is the most distant AGN ever detected at very, very high energies. And this is especially important towards this goal of the CTAO that I commented before of expanding the boundary of the observable gamma ray universe. Still, we haven't broken yet this frontier of Redshift 1, but we see that already with one single telescope, we are very close to doing so. And as soon as we have the 4 LSTs fully operating, this boundary will for sure be broken. So this source was detected in 2023. It actually started flaring in November 2023, when unluckily we couldn't observe because it was the full moon period when the Cherenkov telescopes cannot operate. But it flared again in December 2023, where we managed to observe the source and detect it. This light curve would be is constructed with Fermilab data, and you can see not only how the source is flaring, but also how hard its gamma ray spectrum was, which really gave us the perfect conditions for observing it. And here again you have the Fermi light curve, and we also were very lucky to have a very good overlap between Fermi-Lat's observations and LST-1's, because Fermi-Lat scans the sky every 3 hours more or less, and we actually got a very good overlap between our observing slots with those from when Fermi-Lat was actually pointing towards this source. And this led to the detection of OP313 in December 2023, already after the first 3 nights of observation, but we continued for, I think it was 10 nights. You can see here the snapshots of the press release and the ATEL of the discovery, which made this, as I commented before, the first scientific discovery of LST-1. Most of its emission, as typical from the few FSRQs that we have detected at very high energies, is located at the low end of the very high energy regime. So basically concentrated up to 200, 250 GeV. And you can see here the signal distributed in energy ranges. These are simply what we call θ² plots. It's just a distribution of the detected gamma ray events with respect to the squared angular distance from the position of the source, and you can see a clear excess at the expected position of OP313. But above 250 GeV, we basically see nothing, and this is because its emission, as expected, is strongly attenuated, mainly because of the EBL. But we are also testing possible scenarios where the emission of this source is self-absorbed, as typically assumed for FSRQs as one of the reasons for not being detected at very high energies. And actually, these observations are also important for other studies, such as setting constraints to the EBL. On the right, you see a plot that I extracted from Dominguez and collaborators, 2024, where they represent basically the frontier of the transparent and opaque universe. So when the optical depth of the EBL is 1. And you can see the highest photon detected from every 4 lakh blazar in the Fermi catalog. And you see how deep into the opaque universe we've gone with these observations of OP313. So with these observations, we can really put to test and set competitive constraints to the EBL from direct gamma ray observations at Redshift 1. And this is one of the few sources that so far allowed to do this. So the results on the EBL constraints can be very, very powerful here. And not only that, but we have been continuing observing OP313 with LST1 over the whole year 2024. You see here just a piece of the Fermi light curve. As you can see, even after the first detection in December 2023, it kept going up and down, showing several recurrent flares that we have supported as much as possible with multi-weighted follow-up, and we aim also to do a long-term study of the evolution of the source. And actually, this some of the flares that this source has shown in the past couple of years have been amongst the top most luminous AGN flares ever observed by the LAT. And this culminated actually this January, so 1 month ago, more or less, with the second most luminous flare ever detected by the LAT ever coming from any AGN. And again, being detected by, in this case, not only LST1 and MAGIC, but also Veritas, which proves actually how remarkable this event was, because Veritas, as a system of smaller telescopes with respect to the sizes of MAGIC and LST1, has a slightly higher energy threshold. So them being able to detect such a soft source is really really speaks of how huge this flare was. And now to conclude very briefly, I will show some overview on a tool that we have been developing for this new generation of telescopes. But this tool was basically, as I commented before, motivated by the need of incorporating multi-wavelength observations to our studies. So we often support with multi-wavelength observations our MAGIC and LST1 data. So first of all, we as a community, we are developing as a standard tool for the new generation this GammaPy package. It is a Python-based package which incorporates basically gamma ray analysis tools, not only for CTAO and LST1, but also even for the current generation of telescopes. So MAGIC, HESS, Veritas, even the LAT, and even multi-wavelength facilities. Even X-ray observations can be incorporated to GammaPy, and if you do some fine-tuning, even lower energy observations, so optical, UV, etc. And this is an open package, of course, and it's still under development, but constantly upgraded and maintained. And as I said, for us studying and working on the AGN and Blazar field, we always need to support our very high energy observations with multi-wavelength data, which usually involve, as I comment here, a large ensemble of instruments, of data, and facilities that are usually treated separately. And this comes actually with a series of issues and caveats. For example, in many observations, simply instrument responses are ignored. Astrophysical backgrounds are not always properly characterized or statistically or taken into account in a statistically correct way. For example, when interpreting the proton emission of these sources, we typically don't account properly for upper limits, which are either ignored or fitted by hand, and some assumptions are needed in order to construct these spectral models. So in an effort led in this case by Mireia Nievas from IAC in Tenerife, we have been developing this multi-wavelength analysis workflow incorporated in GammaPy with the aim of incorporating not only LST and Fermi data, but also X-ray, UV, and optical data into the analysis in a comprehensive and consistent way. So the main two goals of this package would be publishing beam event data from optical to gamma rays, so expanding more than 11 orders of magnitude in energy or frequency. And the second goal would be performing spectral characterization based on a full forward folding method. So taking into account the instrumental response functions of every telescope, characterizing properly or as properly as we can astrophysical backgrounds, and from an event point of view, an event-like point of view. So from the very so keeping the model and the extraction of the broadband spectrum as physical as possible, instead of using these non-physical flux points that, as I said, comes with this series of issues. So far, we have incorporated into the pipeline Fermilab data, NuStar data, also Swift, both from the XRT X-ray instrument and the UV optical U-Bot instrument. But we've also managed to incorporate optical telescopes. Not only, I'm showing here the Liverpool telescope as an example, but we have incorporated others, and not only photometry, but actually also polarimetry. So taking into we are taking into account all the features that we can from optical telescopes and incorporating them into this multi-band forward folding for extracting the broadband spectrum of sources from a physically motivated point of view. And this is an example of what we get, actually, again, for OP313, where we can extract the broadband SCD, in this case from optical to high energy gamma rays with Fermi, with this physically motivated spectral model and this full forward folding method. And actually, it was cross-checked with the typical flux point approach. It is, of course, in this case, consistent, but as I said, more physically accurate and taking into account all the things that come to play in this kind of data analysis. And this actually has already been published earlier this year. And actually, Mireia, who led this effort, has given a couple of months ago at another seminar, actually at IAA in Granada, showing more details about this topic. So if you are interested or you want some more information, I really recommend you to go to the YouTube page where the IAA seminars are recorded, and check the whole talk. And finally, to conclude, I just wanted to give some couple of perspectives on what CTAO will represent for the near future of the field, and in the case of and specifically in the case of extragalactic physics at very high energies. And I want to come back to this graph of the evolution of the number of sources that we have managed to detect in the very high energy gamma ray field. And as I said at the beginning of the talk, we are actually kind of in a plateau with this generation. We are not discovering so many sources already because we are reaching the limit of sensitivity of our instruments, and we have managed to detect so far more than 300 of sources. What CTAO will bring to the table is really a revolution in the number of sources that we will be able to observe. You see on the right, not in the same format, but an histogram on the expected distribution of sources to be detected with CTAO in the top panel with respect to the luminosity of the with respect to the flux, the energy flux of the sources. Sorry. And on the bottom panel, actually the number of sources detected by the current generation. So the amount of the increase in the number of sources that CTA will bring is really huge and will enable a lot of studies that so far have been simply impossible. For example, the improved energy resolution, improved sensitivity will allow us to have more detailed studies on the origin of the gamma ray emission, as leptonic and hadronic scenarios are expected to have different features at the highest energies, and so far, simply because we are limited by the sensitivity of the current observatories, simply we cannot do this kind of studies yet. We have not managed to clearly distinguish between the leptonic and hadronic scenarios so far. CTAO will also bring more detailed EBL studies and EBL constraints through direct gamma ray observations. The example of OP313 that I mentioned before is already the proof of these kind of studies. It will bring to the table population studies that simply were not a possibility so far, because we don't know yet so many sources, and most of the agents and blazars that we know them basically. We've discovered them basically during a flaring state, so we are highly biased towards flaring states in blazars. So we do not really have the tools now to perform these detailed population studies. We can aim for detecting more of these remarkable fast variability events that, as I said a few times during the talk, challenge the particle acceleration processes that are often observed or assumed in blazar jets. And they will also offer more detailed, for instance, ultra-high energy cosmic ray studies. We might be able to distinguish between gamma ray, between emission produced by induced cascades induced by ultra-high energy cosmic rays or induced by gamma rays, for example, and many other things. As I said at the beginning, we can do dark matter searches, we can do action light particle searches, intergalactic magnetic field studies. So CTAO will really bring a lot of new information to the field. And as a final remark, I just wanted to conclude with a few words. First of all, as I just said now, CTAO will really bring a revolution to the very high energy gamma ray astronomy field, but it is in a way already the present of the field, as we already have LST-1 operating and obtaining interesting scientific results. And especially these successful TO campaigns and with a special mention to the detection of OP313, which is, as I said, a very important milestone and a proof of concept for this new generation of telescopes that really aims to push the boundary of the known very high energy gamma ray universe. And as a closing point, I just wanted to remind you that CTAO will soon be available, will soon be an open observatory. So think what CTAO can do for you and for your science, because it will be accessible for all the community. And with this, I finish, and thank you very much. And I'll be taking questions.
Thank you very much, Jorge. Thanks for the nice and thorough overview of CTAO. Let's see if there is any question first from online, from the audience. You can raise your hand or unmute directly yourself. But well, meanwhile we wait, maybe I can start with very general. So you said soon. What is this soon? Can you give us some timeline? You show that more telescopes are already in place in the CTAO North. So what
yes. So for the let me go back to the. So for the northern side, which is the one I'm basically familiar with, and I have more information. In principle, by the end of this year, the construction of the 3 remaining LSTs should be completed, either the end of this year or at most, in principle, beginning of 2026. So yeah, by the end of the year, we should already have the most powerful Cherenkov observatory in the world. Now, in the northern side, there will be also, I don't remember the exact number, but MSTs, medium-sized telescopes of, I think it's 12-meter diameter dish. And those are still not under construction, so it will take a bit more. But yeah, by the end of this year or beginning of the next one, as soon as the 4 LSTs are built, we should already have much higher sensitivity than the current generation of telescopes, so than MAGIC has and Veritas. For the southern side, things are a bit more delayed. So for that, I do not have a timeline actually.
Thanks. Any other question? Sí, yes, Ivan.
Hello, very nice talk, Jorge. Thanks a lot. I was just wondering if you could give a little bit more of detail on the physical processes you were considering for this time-dependent SNG of BLAC. So which kind of scenarios and models you are considering for the different time ranges that you are using for the fitting?
Yeah, so well, first of all, for selecting like kind of the snapshots that we are modeling, since unluckily for us in this first half roughly of the light curve, we have quite a poor coverage in X-rays and UV. This first part of the emission of the flare is a bit poorly constrained. However, it's true that is the part that is more stable, so it's not that big of a deal. But just to mention, for choosing these snapshots, we have used a Bayesian block analysis based on the very high energy gamma ray emission from observed by LST1. So we have grouped the data into periods in which the emission as seen by LST1 is compatible with being roughly constant. So this led us to basically 10 Bayesian blocks to model the evolution of the flare. Some of them have a larger duration. For example, the first one you see that is roughly constant, so it accumulates many days. But for example, for, the two brightest nights by themselves are 2 Bayesian blocks. So the duration of the blocks, it really depends on the average emission. For the scenarios that we are considering, for the emission processes, purely leptonic. This is mainly motivated by IXP results, as you know. Also, unluckily for us, for the LST side, one of the observations of IXP, I don't remember if it's the one published by Pearson and collaborators or Mireia and collaborators, was happened actually, I think it was 2-3 days after LST stopped observing during this flare. So it was quite unlucky for us, but yeah, still the results for IXP suggest or favor a leptonic scenario. So that's what we are considering for the nature of the gamma ray emission. Now, for the, let's say, morphology of the jet, we started trying with a one-zone leptonic scenario. It simply could not fit the data because if we want to reproduce correctly the synchrotron emission, then the electrons are simply not energetic enough to produce the gamma ray emission that we observe. So that's impossible to do with one-zone models. So we had to move either to two-zone models or this one-zone plus external Compton. The thing about the one-zone with external Compton emission is that, well, first of all, this scenario couldn't reproduce very well, very precisely as well as for the one-zone the emission, but it also would need extremely large Doppler factors and the emitting region size is very, very, very compact. So reproducing the broadband emission from radio to very high energy gamma rays with an emitting region size on the order of 10 to the 14 centimeters is practically impossible. So we moved to some model in which this compact region, we are trying to motivate it in this way in which this compact region is basically a magnetic reconnection region. And this magnetic reconnection scenario comes basically motivated by the variability timescale. Other acceleration processes have a lot of troubles reproducing or explaining this very fast variability. Even shock acceleration for these very, very short timescales needs huge Lorentz factors. So it's really challenging, yeah.
Thank you very much. I think this answer already to Ivan's question. I may have a follow-up on this actually. Can you go back to the light curves plot?
Yes.
Here, yeah.
Mm-hmm.
It's, well, I understand you have few points, but it looks like to me that you have kind of a delay between the Fermi light curve and the LST light curve. So is this kind of expected in your model?
We are evaluating possible delays. Looking at the Fermi light curve, I mean, it's tricky because actually this very bright night in Fermi, well, night observation in Fermi, it was actually quite unlucky for us because even if it seems simultaneous with an LST observation, I have to say the LST light curve is beamed with a 12-hour beaming. And actually this brightest point in Fermi coincides with daytime in Spain, so we could not observe by then. So this huge peak in Fermi, we might have missed it in very high energies. We are also considering the possibility of being delayed, and we are actually evaluating this. But so far, I mean, it's something that we have ongoing right now, but could be both things. Could be that either we missed this huge spike or that there is really a delayed emission. But in case of in case there is in the event of this delay being real, this can in principle could be incorporated into the models, because actually the Fermi emission, these, as I said, these are preliminary, a bit outdated models, and actually in the interpretation that we are giving right now, the Fermi emission in principle could come from, it's possible to model the broadband emission in a way in which the Fermi emission and the very high energy gamma ray emission come from two different regions of the jet. They don't need to come from the same as in these examples I'm showing here. So if there's a delay, it could be accommodated in the models that we are performing, yes.
Okay. So one last question, if not, I don't see any raised hand, then I think we can stop here, and thank you again for
Thank you very much.
that talk.